and then get back to it. All right, so let's just get started. Good afternoon, everyone. My name is Femi. So this evening, I'll be talking us through meta-analysis in SPSS. I hope you can all still see my screen and you can all hear me clearly. If you can't, just put something in the chat box and I'll be looking at it from time to time. If you have questions as well, just pop them in the chat box and then I would take a look and respond.
We can hear you clearly, sir.
Okay, all right, excellent. All right. Okay, so let's just go on then. So I'm sure this is not the first class you're having on meta-analysis. Many concepts are already familiar to you at the moment. So SPSS is for those of us who are, well, to use the word lazy, who prefer the point and click method instead of going all through the R method, coding and all of that. So I'll just walk us through how we do meta-analysis in SPSS very quickly this evening. All right, so we'll start right away. So meta-analysis of dichotomous outcomes in SPSS. Now, when we conduct meta-analysis on SPSS, when you want to use the dichotomous outcomes, you have different studies reporting risk ratios, odds ratios, hazard ratios. Now, while you are pulling your studies, when you are getting your studies together, when you are gathering your data, it's important for you to pull studies that report the same kind of estimates. For instance, you cannot pull a study reporting risk ratio and pull the result of another study reporting hazard ratio and odds ratio. So it all just gets kind of mixed up. So you need to identify the estimates that each of these studies are reporting, and that is what you need to pull. And you need to make sure, okay, someone said I should consider presentation mode. Better now?
Yeah, this is great. Thank you.
Yes, sir, it's better now.
Excellent. Sorry. So you need to make sure that you are pulling studies that report the same kind of estimate. In cases where these studies don't report this estimate, you might have to do the computing yourself if you have resources or the data to do the computing. So the meta-analysis for dichotomous outcomes can be, done in a number of ways. You can either use the raw data from the study or already provided calculated effect sizes. So I hope we all have our SPSS launched and opened on our computer. The slides are very clear, so you will be able to walk through all of the processes very easily without any difficulties. So depending on the type of weight that we use, we can either use fixed effect meta-analysis or random effect meta-analysis. All right. So for the fixed effect meta-analysis, we assume, the assumption is, all of the studies have the same causal effect, compared to the random effect meta-analysis, where we assume that each study has a different causal effect. So you will see that if you use the same set of data and you do a fixed effect meta-analysis and then you go ahead and do a random effect meta-analysis, you will get different results because they are, you are using different parameters. While the fixed effect assumes that all the studies have the same causal effect, the random effect does the opposite, assumes that all of the studies have different causal effect. So your meta-analysis for a random effect meta-analysis cannot just be you putting together the average of the point estimate from the study compared to how you do it on the fixed effect. No. As we go on, when we do the actual thing, you will see how this figure change, and then you'll be able to probably appreciate it better when we do that. So I reckon that all of us have this metadat. Dr. Abioye sent out an Excel spreadsheet, metadat. Is there anyone who doesn't have this? You can just put it in the chat box and then we can see how to navigate that. So if you don't have metadat, just signify, okay, I think everyone has it then. So let's just go ahead and just work on it and see what exactly we are talking about. So we want to understand something from this metadat. We want to understand whether media campaigns increase the proportion of participants in a particular sample who consume up to 5 servings of fruits and vegetables a day. So
sorry, one sec. I just
okay.
uploaded the metadata file in the chat, so people who don't have it can download it from there.
Thank you very much, our gracious host. All right. So we are interested in understanding something from the metadata spreadsheet, the data that has been gathered there. We want to see whether media campaigns increase the proportion of participants who consume up to 5 servings of fruit and vegetables a day. So let us all launch our SPSS and import the data. So the first thing you have to do is to import the data. So for you to import the data after launching the SPSS, you just go ahead and click on File. File is on the top left corner of your SPSS screen. You click on File, you click on Import Data, and then you click on Excel. And then you just have to look for where you have stored the metadata spreadsheet and import it into your SPSS app. Is that clear? So I'll just give us like a minute or two to do that. So I'll repeat it again. Just open your SPSS app, launch it, click on File on the top left corner, click on Import Data, click on Excel, and then you just have to look for where you saved the file. So I will be needing some feedback from us from time to time, either verbal or you type in the chat box so I know when to proceed and when to halt. Have we been able to do this? Have we imported our file? You can just give me some thumbs up or something in the chat box so I know we've done that. It's not impute, it's import. Import data, importer, exporter, import data. So Miriam, it's import. Just look at the top left corner of your SPSS, click on File, click on Import Data, click on Excel, and then your data automatically just gets in. It appears. All right. So after importing your data, I want to start the meta-analysis. So I want you guys to click on Analyze. Analyze is at the top of your screen. Click on Meta-Analysis.
Hello.
Yes.
Sorry, please. I still can't get the import data. I clicked on my file. It's not showing me any import data.
So when you
Should I
click on
show it?
File, yes.
Yeah, let me share my screen.
Let me just get my setup to.
I was about to share a screenshot with her.
All right, so this is file and this is import data. I hope you can see my screen.
Yes.
Yes.
Okay, so if you click import data and then this is Excel. So you will have to move your cursor all the way and then come to Excel. So if you click Excel, you will have to navigate, like the instructor said, to where you have the file saved. So I have it saved here in course material. So you will have to navigate by looking all the way. So if it's in your documents, wherever it is that you have saved, okay? So this is where I have it saved. If you have saved it in downloads, you can find it there. And then you click the file and click open. So because
Sorry,
I
I think
already have it open.
I think maybe my just like somebody said, maybe my version is different. It's the 16th. It's the 16th edition. So
Okay.
I will catch up. I'll catch up. I can't
right.
still find it. Yes.
Okay. All right. You can try open too and see if it works.
All right. So is it all right if we move on?
Yes.
Okay.
Yes, we can continue.
All right. So now we'll go to we want to do the meta-analysis proper now. So just click on Analyze. When you click on Analyze, click on Meta-analysis. When you click on Meta-analysis, because we are working with dichotomous outcomes here, which is somewhat synonymous to binary outcomes, so click on Binary Outcomes. And then because we are using pre-calculated effect sizes, our main instructor has been very gracious, as designed a very nice spreadsheet for us with all the calculated effect sizes. So we can just go ahead and use that. So click on pre-calculated effect size. So when you open it, you will see different boxes requiring to put in different information. So all of the boxes will be empty in the initial phase. You will see effect size, you will see standard area of variance, you will see study ID, and you will see study label. Can we all see that?
So, Femi, can you?
No, we can't. Can you share your? Yes,
should we
I
do
think
this?
you should
Let's
share.
do this.
Yes.
You will speak me through it. Okay, you just be speaking, and then I'll be demonstrating. Should we do that?
Okay.
Yeah, because I think it will be easier if people see what.
All right.
Okay.
So
right.
Let me take down my screen then. Okay, so do you want to share your screen? All right.
Yeah.
So
okay.
Let's click on Analyze.
So this is Analyze.
Then Meta-analysis. Then Binary Outcomes, because we are working with binary outcomes in this situation. So we click on pre-calculated effect size. All right, so we can see the different sections. We can see effect size, we can see standard error variance, we can see study ID, and we can see study label. So we need to populate each of these boxes. So how do we go ahead and populate each of these boxes? You click on—
Hello, sir.
Yes.
Sir, please, sorry to interrupt. I can't find the meta-analysis option. I'm using SPSS version 26. I don't know.
So the meta-analysis option, I think, is only available on the very, very recent SPSS versions. I don't know how recent SPSS version 26 is. It's available on the very recent ones. So I'm not sure you would find it on version 26 if it's not recent, unfortunately. But I think so. There's a trial version available.
The version we're using now is 29.
Yeah.
So that's what the problem is. Dr. Abiy, what do we think? There's a trial.
I don't know. Can they make a quick setup?
Yeah, so there's a free trial version available. Is it possible that we give you maybe 5 minutes to download it and just set it up? Is that something we can afford, Dr. Abiy?
I'm not sure. I think that he should go ahead. Whoever is having trouble finding meta-analysis on their SPSS should go ahead and download it and try to catch up with us. We can spend some time after to just try to catch them up. But, you know, we're already 20 minutes into the class, and I don't think we can wait further.
Okay. All right. So we'll just go ahead then. So we need to populate each of the boxes there for us to be able to run our meta-analysis. So I want you to scroll and look for log ES. I want you to scroll and look for log ES. Just scroll until you find log ES. So click on log ES and then click on that blue arrow to put log ES in that section. Okay, so is that clear? Is everyone following? Then I want us to also do the same thing for the standard error section. So I want you to go ahead and look for SE log ES, which stands for standard error of the log of the effect size. And then Also click on that to put in that section as well, under standard error. Okay, thank you, excellent. So the next box that we need to populate is the one that says the study label. So click on author year and put that in as your study label, and then put in study ID as your study ID as well. So I think when we do that, we must have successfully populated all of the important boxes. Okay, and then just click OK to run the meta-analysis.
Did everybody get that?
Yes, I got that.
Yes, I got.
All right, great.
Is there anyone who is lost? Sorry.
If you are lost, just put it in
Speak
the
up
chat
now,
box,
yeah.
and we'll find you.
Perfect. Let's keep going.
Okay, all right. So let's just go on. So I believe all of us would have seen our results by now. You'll see two tables, kind of, one that says meta-analysis summary, the other one that says case processing summary. You have the number of studies that have been included there. You have the you have what has been used as the weight, your model, which is the phase defect model, the effect size measure that you are considering, which is the logarithm of the effect size, your outcome type, binary, same as dichotomous outcomes. So, all right. Now, you would see that your effect size, in this case, you will have figures of 0.330. You will have your lower confidence interval to be 0.280 and the upper confidence interval to be 0.38. Does anyone have different results? I should probably go back to sharing my screen.
Yeah, I think maybe share screen. I think we might be using different versions of the data. Oh, sorry, I did random effects.
Okay, not binary.
Not fixed effects. I didn't change this to fixed effects.
Okay.
Okay. All right. So let me click OK again. Right. That's it. So 0.330.
So yes, so we can all appreciate the figures now. You have effect size of 0.330, you have lower confidence interval of 0.280, and you have the upper confidence interval of 0.380. So the question now is, how do we interpret these figures? How are these figures interpreted? Don't let us forget that what we have here is based on the logarithm. So for us to convert this effect size to the actual risk ratio, we need to exponentiate it. So if you have a calculator or you have your phone there, just take your phone or your calculator, open up your calculator on your phone. You would see the scientific aspect of your calculator where you just click on the letter E. Do you understand what I'm talking about? Every smartphone has a calculator. The calculators usually have a scientific part of it. And under the scientific part of it, you will see letter E. If you can look at my video, I have it just here, this. All right, so click on that letter E and put your logarithm in the bracket and exponentiate it. It will give you a value of 1.39. Do the same thing for your lower confidence interval and do the same thing for your upper confidence interval as well. So that will be you exponentiating the results. So exponentiating the results is what gives you the actual risk ratio that you intend to work with. And now the next question is, how are these findings interpreted?
Sorry, before you go, I just want to quickly point out that this is an important difference between SPSS and RevMan. Yesterday, when we looked at RevMan, even though the numbers that we put in are the log numbers, when RevMan gave us the output, it had exponentiated it for us. In SPSS, you have to do it yourself. So it's important to understand those differences between the different tools. Okay. Thank you.
Okay. All right. So we have put together a total of 13 studies trying to check whether media campaigns are associated in any way with the intake of greater than 5 servings of fruits and vegetables daily. So from our figures here, what we put from SPSS, we have seen that our beta coefficient is 0.330. What does beta coefficient mean? Does anyone have any idea what that means when we say beta coefficient? If you have an idea, you can just unmute and then you can just speak. All right. No one.
I think,
Okay.
is that not the pool estimate?
Okay, so it has a specific meaning actually.
I think it's like the coefficient of the linear regression.
Good. So how do you interpret it? What's the interpretation?
Well, usually it means that like if one variable increases by a value, like let's say like a 1 point of a value, the other one will now increase by 0.330.
Excellent. Yes. So let me just go ahead and share my screen again. So for every unit increase in media campaign, your intake of greater than or equal to 5 servings of fruit increases by 0.330. So that's just what the beta coefficient means. For every unit increase in your in the media campaigns, there is an increase of 0.330 in number of those who take greater than or equal to 5 servings of fruit. And your risk ratio here is 1.39. A risk ratio of 1.39 is obviously favoring media campaigns, particularly because your confidence interval does not include the null value of 1. Don't forget, risk ratio is something divided by something. Now, because you are dividing one figure by another figure, if it includes 1 in your confidence interval, so let's take, for instance, let's say your confidence interval is 0.28 to 1. It means that it has already included the null value of 1. So, an actual relationship might not exist between taking 5 servings of, between media campaigns and taking greater than or equal to 5 servings of fruits and vegetables daily. If your confidence interval does not include the null value of 1, then you can reject the null hypothesis, saying that there is no association between media campaigns and intake of 5 servings of fruit and vegetables. So before you go ahead with your analysis, in your mind, you need to sort of define what your null hypothesis is. You need to define what your alternate hypothesis is. Your null hypothesis is going to be, oh, there is no association between media campaigns and intake of greater than or equal to 5 daily servings of fruit and vegetables. Your alternate hypothesis is, oh, there is an association between media campaigns and intake of these 5 servings of fruits and vegetables. And after defining your null and alternate hypothesis, the next thing for you to do after you run your meta-analysis is for you to examine the confidence interval. Your null hypothesis in this case is going to be 1. That's the null value, it's 1. You now check your confidence interval. Does this include a value of 1 or does this exclude a value of 1? If it includes a value of 1, then there might be no relationship between intake of 5 servings of fruits and media campaigns. If it doesn't include a null value of 1, then you can reject the null hypothesis. I hope that's clear, and conclude that media campaigns are associated with intake of 5 daily servings of fruits and vegetables. We will still go over this concept over again, particularly when we get to the continuous outcomes as well. So I think we can move on if there are no questions.
Yeah, I have a question, please.
Yes.
Is there any way one can make SPSS bring up forest plots? And
yes,
maybe funnel.
So we are still going to get to that part of bringing up the funnel plot and the forest plots. Yes, that's part of this class.
All
right. Okay, so we're going to do essentially something similar to what we did before, but this time around, we are using random effect meta-analysis instead of fixed effect. So I want us to go back to our SPSS. There's no need for you to import the data again this time because you already have it in your SPSS already. So you just be running through the processes that you already have on the screen. Yeah. So just click on Analyze, click on Meta-Analysis. We are still using binary outcomes, so still click on binary outcomes. We are still using pre-calculated effect size, so click on pre-calculated effect size. Now, under effect size, leave your log ES there. Under standard error, leave the SA of log ES there. Under study ID, same thing that we did before. Under author year, under study label, author year, same as before. But in this case, we are going to click on random effect under model. So there's a section on the right where you see model. Just click on random effects instead of fixed effects like we did before. Then there's a column on the right side written in blue, highlighted in blue. You see where it says inference. So click on inference. Check the radio box that says REML, restricted maximum likelihood. Click continue and then click OK.
What about the effect? Is it odd ratio or risk ratio?
Pardon?
The effect size.
You still use log risk ratio. Log risk ratio. We are working with risk ratio. Yes, so log risk ratio. All right, so have we all finished that? Have we arrived at the final answer? So you would see that your figure, your answers this time around are different from what you got for the fixed effect meta-analysis, even though you are using the same set of data. Can we see the difference? So one is for the random effects, that was the first one, and that was the second one we did. The other one is for the fixed effect. The figures are quite different, okay? And I mean, these figures are different because we have used two different methods essentially. So you are unlikely to get the same result for both of them. Now, in the real world, I think we usually, I mean, most times the random effect meta-analysis is what is done most times, so that you just pull estimates using different weights, different effect sizes, so you can account for all of the studies, account for all of their results. So most times is the random effect meta-analysis that is usually done, oftentimes. Okay, so is anyone lagging behind? Is there anyone who is lagging, or can we go on to the next part of the class? Is there anyone who has been unable to carry out this fixed and random effect meta-analysis? Anyone having difficulties with doing that? Okay, no comment. So I take it everyone is getting it quite easily. All right, so I'll just go back to sharing my screen now. All right, so someone asked a question about forest plots the other time, said, can we use SPSS to generate forest plots? Yes, the answer is yes, absolutely. You can use SPSS to generate forest plots. And we're going to be doing that in this class as well. So similar to what we did before, just go ahead and click on Analyze all over again, Meta-Analysis, click on Binary Outcomes, click on pre-calculated effect size. Okay, so I want us to click on plot because we have just finished one meta-analysis, so you might not need to populate those boxes all over again. Just go ahead and click on plot. Under plots, you will see forest plot, you will see cumulative forest plot, you will see bubble plot, you will see funnel plot, you will see Galbraith plot. So at the moment,
continues sharing the screen.
yeah. So I think Dr. Abioye can take over here. I'm so sorry for the back and forth.
So what do we do next?
All right. So I want us to check some of those boxes under forest plot. After checking forest plot, you will see some other boxes that says effect size. I want you to check that box that says effect size. I also want you to check the box that says confidence interval limits and the box that says weight. So after checking all of those boxes, I want you to click on look at the section that says reference lines. You will see overall effect size, you will see null effect size. I want you to check both boxes. Check both overall effect size and null effect size. And then you will see another section that says annotations. Annotations, that's on the lower left corner of the screen, annotations. So I want you to check heterogeneity and I want you to check test. So click on continue, click on OK, and there you have your wonderful forest plot. Has everyone gotten their forest plot? So we can all see Dr. Abioye's forest plot. Is there anyone who is yet to get his or her forest plot? Okay, I'll take that as a no. So let's go on and just talk about what this forest plot means. So what does this forest plot tell us? We have loads of information on this forest plot. Now, I want you to look at the different features of this forest plot. We can see a blue box. We can see different blue boxes actually of different sizes. The different blue boxes have different sizes. You can see a line, a horizontal line of varying lengths across each blue box. You can see a diamond, a precious diamond, right at the bottom, and a line, horizontal line, just across the diamond as well. We can see a red line, a broken red line, running all the way from the top through the diamond at the bottom. And then we can see another solid, thin gray line running all the way from the top to the bottom as well. So all of these lines are not just there to make the forest plot beautiful. They give you different information. So we need to explore what each of the informations are. Okay, first you have your study IDs on the left. That line, that solid gray thin line that runs from the top to the bottom is called the line of no effect. It's called the line of no effect, and it gives us some information. It tells us whether the results we have relative to the line of no effect, it tells us whether the results we have are in favor of the intervention arm or of the control arm. Let us take, for instance, if you are looking at a study that's talking about maybe mortality, maybe we want to sort of establish a relationship between drinking alcohol and then mortality. So let's say we have two groups. We have a group that drinks a lot of alcohol, and then we have another group that doesn't drink any alcohol. The outcome of interest is mortality. So the line of no effect in that case might be interpreted differently from when you are looking for a favorable outcome. So this is what I mean. The outcome of interest, the outcome that you are desiring, your intervention arm and your control arm determines how you interpret your figures relative to this line of no effect. Now, if you are looking for a favorable outcome, say media campaigns, intake of greater than or equal to 5 servings of fruit daily, if you have most of these boxes to the right, it means it is in favor of the intervention arm. So if you have most of these boxes to the right, like we have now, this is generally in favor of the intervention arm. So it means, oh, from doing our forest plot, we can see that, okay, there's a very high chance that media campaigns favor intake of 5 servings of fruit daily. Now, if the outcome that we are looking at is maybe something like mortality, you would expect most of these blue boxes here to be on your left, on the left of the line of no effect instead, because your outcome of interest is undesirable. So we have to be careful the way we interpret our line of no effect relative to the outcome of interest, whether it's a desirable outcome, whether it's an undesirable outcome. Now, these horizontal lines that run right across each box, they tell us what the confidence interval is. They just give us an idea as to what the confidence interval is. So obviously, the longer the horizontal line, the larger your confidence interval, okay? The longer the horizontal line, the larger your confidence interval. And the diamond at the bottom, the green-shaped diamond at the bottom, is your pooled results. So having put together all of the different studies, all of these different blue boxes, considering their positions, putting them together at one, you get this green diamond down here as your pooled result, also with a confidence interval of its own. So this green diamond is what you have here under overall. You can see the logarithm, 0.38. You can see the lower confidence interval, 0.25. And you can see the higher confidence interval, 0.51. And you can see the red line running all the way from the top to the bottom. Another thing I want you to examine is the weight. Now, the size of these blue boxes, each of these blue boxes, the size is the weight of that particular study. So when you look at the blue box, you will see that the larger ones are studies with more weight. The smaller ones are studies that have very small weight. So let's take, for instance, the second study now, ADB 2018, that has a weight of 10.48. You can see the box is the largest. It's big. And just below it, we have Adejare 2022. You can see the box is small. Another thing I want you to note again, this just have it at the back of your mind, is that oftentimes studies that are large will probably have higher power. When those studies have higher power, these large studies usually have narrower confidence intervals. So you will see that the blue boxes that are big have a very short horizontal line running across them, compared to the tiny boxes that have very long horizontal lines running across them. So the more powerful your study is, the larger the number of participants that you involve, the more statistically powerful your study is, the smaller or narrower your confidence interval would be. So that is why you have so it's not intentionally, it's just something that just happens. So larger studies, higher power studies, studies with more weight have narrower confidence intervals, and then you have shorter horizontal boxes running across them on your forest plot. Smaller studies with lower power have larger confidence intervals typically, and then you have longer horizontal boxes running across them. Okay? All right. So now let us obtain, let us obtain a pooled relative risk. This time around, let us use random effects, and then we are going to be using raw data instead. We are not.
Excuse me.
Yes.
Please, if you don't mind, can you explain the lower left part of this graph where you have the tau squared, the I squared?
So we are still going to get.
Mean?
So yeah. So
okay.
we are still going to get to that part. We'll still be discussing about heterogeneity. Yes, as we go along in this class. for now, just let us get the concept of the forest plot, what these boxes mean, what these lines mean, what these horizontal lines that run across mean. We will still get to the heterogeneity aspect during this class, okay? All right, so let us obtain a correlative risk using random effects meta-analysis, but this time around, we'll be using raw data. We will not be using pre-calculated effect sizes. We will be using raw data. And then we'll see whether there is a difference in the result that we will get. So, Dr. Abioye, are you happy to share this?
Yeah.
All right. So let us click on Analyze. Let us click on Meta-analysis like we've been doing. Let's click on Binary Outcomes. And then this time around, we are clicking on Raw Data. So when we click on raw data, let us click on log of the risk ratio under the effect size. Under model, we are clicking random effects. Under inference, we are clicking on restricted maximum likelihood. Click continue.
Sorry, did you say random effects?
Yes, random effects.
Okay.
All right. So when you look at it, you see that you have two groups. You have treatment group, you have control group. So under treatment group, let us look for exposed case under variables and put that in under success. So you have the treatment group, you have the control group. Each of them has success and failure section. So for success for the treatment group, let's put in exposed case as success. For failure, let's put in exposed non-case as failure. Under the control group, for success, let's put in unexposed case as success. And for failure, let us put in unexposed non-case. Put in author year as your study label, put in study ID as your study ID, and click OK. So essentially what we have done in this raw data under this random effects meta-analysis is, instead of getting the pre-calculated effect sizes that we were given before, the risk ratio, this time around we don't have that. So SPSS is going to compute it for us. Now, these parameters that you're looking at, exposed case, exposed non-case, unexposed case, unexposed non-case, you can liken it to constructing what we call a 2x2 table, where you are looking at, exposed cases, unexposed cases, exposed non-case, and unexposed non-case. So that is exactly what you are putting into SPSS here. It's just like a variant of the 2x2 table that you're imputing. So I want us to run it, click OK, and then you will see that the results are the same. For pre-calculated effect sizes and for raw data, we have the same results. Now, when we adjust for confounders, I hope we all know what confounders are. Is there anyone who doesn't know what a confounder is? Do we all know what confounders are? I don't know how far we've gone in this class. I don't know if all of those concepts have been explained. I can just quickly run through it.
So we explained it in the recordings. We also explained it in the early review, but I'm not sure if you want to explain it quickly. I don't know how much time you have to do that.
I'll just say one or two lines about it. So a confounder is like something else, like a variable that gives like an alternate explanation for the relationship between the intervention and the outcome. Now, there are three major criteria that we always say that a confounder must fulfill for you to call it a confounder. It must be independently associated with the intervention, must be independently associated with the outcome, and then must not be on the causal pathway between intervention and outcome. For example, now, if you are talking about, let me see, if I get a good example as we go on in the class, I'll just probably just chip that in. But yeah, that's essentially what a confounder is in summary. So
You can use cigarette smoking and colon cancer or lung
good.
cancer.
So if we use
The
cigarette
coffee
smoking,
and smoking this thing.
so if we use cigarette smoking and lung cancer, what do you think can confound the relationship between both of them?
Coffee.
Why? Why would coffee confound the relationship between cigarette smoking and lung cancer?
Age can
it should-
confound it.
It should
Age
be
can be a
because
confounder.
when there is
Do people who smoke cigarettes, are they likely to take coffee? Are they likely to drink more coffee?
yeah, a bit. I think so.
Yes,
So
I think
that's
people who smoke cigarettes also take coffee in most cases. Because
It
both of them
was
are
one of the examples
stimulants,
that was shared
prevent
in the
them from
recorded
sleeping.
session.
okay. Well, I don't think that is.
I think we can make use of age as a confounder.
Yeah. So age can confound that relationship actually, because I mean age is independently associated with cigarette smoking, because most likely the older you get, probably the more you smoke. And then age can also, I mean, you hardly find lung cancer in people who are very young. You can hardly find lung cancer in a 2-year-old. So age can be independently associated with both of them. And cigarette smoking does not cause age. So age is not on the causal pathway between cigarette smoking and lung cancer. Sure, you understand? So age can be a possible confounder of relationship between cigarette smoking and lung cancer. Someone said I should quickly run over the explanation between difference between pre-calculated data and raw data. The difference is very simple. For raw data, your risk ratio or your odds ratio or your hazard ratio has not been given to you. You don't have all of those things. You have your raw data, the data that you gathered by yourself. You have not done the calculation for your risk ratio, for your odds ratio, and all of those things just yet. For pre-calculated effect size, pre-calculated data, that has been given to you. You have been given the risk ratio or its logarithm, or you have been given your odds ratio or its logarithm. So that's essentially the difference. It's just that one is sort of like a finished product. That's the pre-calculated data. The raw data is raw. Nothing has been done about it. It's just there in its raw state. Okay? So I think we can move on. All right. So we have gone through forest plots, we have looked at raw data, we have talked briefly about confounders. Now we need to talk about continuous variables. All the while we've been dealing with binary outcomes. Now we'll just talk about meta-analysis of continuous outcomes. I mean, it's nothing special, it's not very different. We are still going to be using the same data set. It's just that we'll be doing it a bit differently this time around, just a bit differently. So I want you to click on Analyze. I want you to click on Meta-analysis. And then this time around, we are going to be using continuous outcomes and pre-calculated effect size. So under model, I want you to click on fixed effects. All right. So under your effect size, I want you to put in MD, search MD on your left. MD is just mean difference. So I want you to put in MD on your left. Under standard error, put in SEM, that's standard error of mean. Put in author year as your study label and put in study ID as your study ID and just click OK.
I want to just quickly say that the SEM variable, we had relabeled it to the standard error of the MD, so SE_MD. So it might look different if you have if you got the file yesterday. It's different from the version that the instructor is using.
All right. So so put in all of those things and just click OK, and you would have your results again. All right. So do we have that? Is there anyone who is lagging? Okay, so I mean, we can see the results very clearly here on Dr. Abioye's screen. And then we can go ahead to interpret what our results mean. So what do we think these results mean? Is there anyone who can interpret this result for us? I am very happy to call on a random person's name if there is no one volunteering. So can we have any volunteer? I mean, we've been talking all day about effect sizes, upper confidence interval, lower confidence interval. So can anyone just give us a brief interpretation of this result? How can we interpret it? What does it mean?
Hello.
Yes, please go on.
So we can say for every unit increase in media campaign, the number of sevens, the number of sevens increases by 0.873. Is it?
Okay.
The number of people that
The number of people
that gets greater than 5 sevens increased by 0.873, I think.
Okay. So what about the confidence interval? What's the meaning of confidence interval?
Well,
now this can be anybody. Yes.
For this one, because the confidence interval for difference should not include 0. So since it doesn't include 0, then I think that's fine.
Excellent. So because in this case we are dealing with mean difference, so I want us to note this so that we don't get it mixed up. Before we dealt with logarithm, we dealt with risk ratio before, sorry. And ratio simply means something over another thing. If we say 3 over 3, that's equal to 1. So 1 is going to be our null value when you are dealing with the ratios. Now, when you are dealing with difference, your null value is not going to be 1. It's going to be 0 because 3 minus 3, for instance, is 0. So that is what your null value is going to be. So I want you to just take note of that. The null value for the ratios is different from the null values of the mean difference, okay? So that is why before you go ahead and start your analysis, you need to either write out or just have it at the back of your mind what your null hypothesis is going to be, what your alternate hypothesis is going to be, and what your null value is going to be. So does anyone know what it means when we say, oh, this thing has 95% confidence interval? Does anyone have an idea what that means? I mean, 95% confidence interval. What does it mean? It has a meaning. Any takers? Yes, speak.
I think if a study is conducted, if a study is conducted, that the probability that the outcome will fall within the interval, that is the probability that the outcome will fall between the interval on the normal curve. That is, if a study is repeated over and over again, the chances of the probability, the outcome will fall within the value, the range on the normal curve, normal distribution curve.
Okay. Any other takers? Does anyone have any?
Yes, it means. Hello?
It means that if you conduct the study 100 times, 95 times out of the 100 times, you are going to get a value that lies between that range of value that you have that make up with confidence interval.
Yes. So that's it. So it means that, I mean, in the general population, I mean, we can be 95% confident that the true effect size in them is going to be between 0.754 and 0.823. So if we run this study 100 times, 95% out of 100 times, you will have it falling between 0.754 and 0.823. Okay, so let's go to heterogeneity. Someone asked the question the other time that, oh, all of those things that were down, all of those things that were written down, heterogeneity, tau squared, I squared, and co, what do they mean? So now, Because we are conducting meta-analysis and systematic reviews, you use different studies. You pull in multiple studies from multiple sources. And obviously, you don't expect all of these studies to have the same characteristics. I mean, they are going to differ definitely. Some of them will differ in the details of the intervention. Oh, we can't see my screen, sorry. Let me just go back to sharing my screen. Sorry. All right. So the studies that we bring together when we do this meta-analysis, all the studies can't be identical. They have different attributes. Some of them, the mean age would differ. While some studies are conducted in the elderly, some may be conducted in children. The clinical characteristics would differ. The outcome details would differ. The intervention details could differ. I mean, if you are looking at, if you are bringing together studies that examine the effect of ceftriaxone, for instance, now on, let me say, toxoplasmosis, you can consider different studies that give it via different routes. While some may give intramuscular ceftriaxone, some may give intravenous ceftriaxone. So all of those things could contribute to heterogeneity. Now, if these differences in these studies are responsible for the differences in the contexts that we see, differences in the effect sizes, we can't call this statistical. And there's a way we can check for this. There's a way we can test it when we are doing our meta-analysis. The two main methods that we use the Q statistic and we use the I-squared statistic. Now, for the Q statistic, it has some limitations. The Q statistic only tells you that, oh, heterogeneity exists. It doesn't tell you to what degree. It doesn't tell you to what extent. So by the time you do your Q statistics, which you are going to do this evening, and you get a p-value less than 0.10, you could say, all right, heterogeneity exists, but you don't know to what extent. But for the I-squared statistic, it could give you an idea as to how much heterogeneity exists. And we have that in this table. So from 0 to 40%, that's limited heterogeneity. 40 to 60%, that's moderate. 60 to 80, that's substantial heterogeneity. And 80 to 100%, that is considerable heterogeneity. Now, the reason why we check for this heterogeneity is we want to know to what extent are these studies different. So if you bring together studies and then you have heterogeneity of, let me say, 0.82, that's like it's 2%. That's considerable heterogeneity. That means something has happened. There are one or two studies there, or even three, that are entirely very different. Now, if you are doing meta-analysis, you are checking for, let's go back to what we've been talking about all day. Effect of media campaign on eating greater than or equal to 5 servings of fruits and vegetables daily. Now, if you conduct this study in children, let's say under 5s, and you conduct this study in adults, and you bring these studies together, that doesn't really make sense, because there's a very high chance that you are going to have considerable heterogeneity because of that stark difference in the population characteristics. So you have to always look at your heterogeneity and think about what could be responsible for it. Are there studies that are fundamentally different from the others that have been included? And then you should decide whether or not you need to exclude or include them in your study. For instance, if you have 6 studies and 5 of them are done in adult or elderly, and 1 is done in under 5s, you may have considerable heterogeneity, and you should consider removing the one done in under 5s from your meta-analysis. Okay. All right. So let us go back to.
So we have a hand raised.
Okay.
I see Kabir Musa's hands raised. I'm not sure if he still has a question. It's been raised for a while. Maybe to
okay, please speak, Kabir
I
Musa.
wanted to answer a question, but it's over. Someone has
Oh,
done.
apologies. Sorry about that. Sorry.
Yeah.
All right. So what I want us to focus on this slide is look at heterogeneity. Look at where it says I squared. Can we see what it says there? 0.82. So that is considerable heterogeneity. Now, the question is, now that we have considerable heterogeneity, what is the next thing that we do? So how do we tackle this considerable heterogeneity? Now we need to use a method we call meta-regression and prediction intervals. So I want us to go back to our first meta-analysis of dichotomous outcomes. Okay. It's pretty much the same thing that we have done before, just some slight differences. So Dr. Abiy might need to take over sharing the screen at this point again. So what are we doing with this meta-regression and prediction interval? We are trying to see what is probably responsible for this considerable heterogeneity that we have in this study. We want to try and explore, we want to try and find out. So you click on Analyze, you click on Meta-analysis, and in this case, you are going to be clicking on Meta-regression. So you want to consider, oh, what has happened in each country in this case, because we are going to impute country under factor. So we want to see what has happened based on country. So after clicking on meta-analysis, clicking on meta-regression, impute log ES under your effect size, impute SE log ES under your standard error, and impute country X under your factor. So click on inference. Under inference, click on restricted maximum likelihood. Click on continue. Print. Click on display exponentiated statistics. Click continue. And then click OK. And you should have this. So are we all there? So some people are asking that, how can we get version 29? I know there's a trial version available on the IBM website, so you can get access to it for about 30 days. So you can just, after this class, you can go ahead and download it and just try out all of these things on your own all over again. Just
sorry, sir, what about IBM 26?
I'm not sure you can do all of these things on IBM 26. I don't think so.
Okay.
Yes,
okay.
So you might need to get the most recent version.
Okay.
Yeah, so I should just highlight that one of the reasons why we are teaching 3 softwares, in this class, RevMan, SPSS, and R, is so that you can have alternatives. We understand that SPSS might not be easily accessible to everybody. You might need to pay, once the trial elapses, and you might not want to do that. So RevMan is free, R is free. So if you can't get SPSS, don't bother too much about it. If you can, then this is great. You can learn the software. If you cannot get SPSS, then RevMan works great as well. You can also download the trial version and use that to practice. We sent the website in email, but you can also check on Google. It should be easy to find. Thank you.
Okay, thank you very much, sir.
Thank you. So we have, we get this as our result. Can we all see my screen?
Yes, sir.
All right. So we have done our meta regression and we checked the prediction intervals. So we have 2 different results here. The first one at the top, you can see chi-square Q statistic. So how do we interpret this chi-square Q statistic of 0.044? We talked about it briefly a few slides earlier. I'll just take us back there. So we can see that Q statistic, we say heterogeneity exists if the p-value is less than 0.10. And obviously 0.044 is less than 0.10. So there is heterogeneity. There's some residual heterogeneity in this study. Now, how do you now interpret these prediction intervals? What we have done with these prediction intervals is we are trying to find out what is responsible for this heterogeneity. Now, with your I-square statistic, your I-square, as I mentioned to you before, tells you to what degree heterogeneity exists, okay? And then, because, we don't expect all the studies to be identical. We expect some variability, but the variability should be reasonable, should probably be attributable to only sampling errors instead, and not stark differences in the studies. So I want us to look at this table that says parameter estimates and look at the section, the column that says significant two-tailed, and look at it from the top all the way down. One of them obviously stands out. Which one of them stands out? Any guesses?
0.005.
0.005, excellent. And that belongs to which country? Tanzania. That's country 4, okay? So it means that, the data we have gotten from Tanzania, it's quite different to what we have from the other studies. It's 0.005. It's quite significant, okay? That's significant p-value. So we need to start thinking as to why that has happened, okay? Why does Tanzania have this significant p-value of 0.005 and the others don't? It could be for a number of reasons, okay? It could be because they have used maybe entirely different set of participants. It could be because the population characteristics of their participants was very different. It could be for loads of reasons. So we just need to think about what the possible reasons could be for Tanzania, okay? While it has that significant p-value, all right? These are some other reasons here in the slide. It could be due to the design of the interventions. It could be due to the populations targeted by the interventions that we mentioned already. It could be due to the sample sizes, okay? So you just need to try and find out why Tanzania is very different from the rest, all right? So moving on, we'll just briefly touch on bias and sensitivity analysis. Now, bias, you have to check for what we call publication bias after doing your meta-analysis. What is publication bias? So publication bias is present if your study is more likely to get published because of the results, okay? So, there have been many cases of falsification of data forgery, people just, concocting data and then looking for associations or causality where they don't truly exist. So all of those things could potentially lead to publication bias. And then you need to check your study, your meta-analysis for publication bias before you go ahead and submit it for meta-analysis, for publication, sorry. Now, we check it in two ways. We check it with two methods. The first method, we use the funnel plot, and then another method is we use the Eggers test. In reality, we have another alternative, which is the Beck's test, but that's not usually used. So oftentimes we just stick with the funnel plot and we look at the Eggers test as well. What do we look for in the funnel plot? We look for symmetry or asymmetry. When there is asymmetry in the study, there's a high chance there's some publication bias in your study. Now, one thing you have to have at the back of your mind with epidemiology is you have to consider some alternate reasons why you have what you have, why you have the kind of results that you have. You have to be careful in interpreting your results. You oftentimes cannot just make blanket statements and say, oh, because this is this, then this is that. You cannot just say, because the funnel plot is asymmetrical, then it automatically means you're 100% sure there's publication bias. So There are some other reasons that could make your funnel plot asymmetrical, and we'll just touch on that later on, just very briefly, because it's not really what's in the scope of this module, but still important for you to know that. So we are going to create our own funnel plots, all right? And then Dr. Abi may need to take over again at this point. Is Dr. Abi still with us?
I am. I already shared my screen.
Okay, all right, thank you.
Yeah.
So I want us to click on Analyze, Meta-analysis, Binary Outcomes, Pre-calculated effect size, then click on Plot, click on Funnel Plot. And under the section that says Y-axis values, just click on standard error. Are we out there? So analyze, meta-analysis, binary outcomes, pre-calculated effect size. We still have our details there. So under plot, funnel plot, you click on funnel plot, and under what, just check the funnel plot box, and under y-axis value, standard error, click continue and click OK. So I suppose we can also see the funnel plot now.
Yes, sir.
All right. So how do we interpret this funnel plot? Now, there are some things, I'll just do a general explanation of what the funnel plot is and then what we should look out for. Now, on the funnel plot, you have some studies at the top. You have some studies below. There's a reason it's like that. So studies that have higher power, the larger studies, studies you typically find at the top, just sort of coming together, all of them at the top. While the studies with lower power, the smaller studies you find down, just below here, okay? And sometimes it's difficult to tell whether the study is symmetrical or asymmetrical by just looking at the funnel plot. What you do expect for symmetrical studies is you expect the studies to sort of come together at the top and then evenly spread out kind of towards the bottom, giving you the shape of like an inverted funnel. So you have studies at the top, some kind of coming together, and then studies spread out below, giving you the shape of an inverted funnel. And that gives you an idea as to whether the studies are symmetrical or asymmetrical. Okay? Now, if there is publication bias, you are going to have an asymmetrical study. If there is no publication bias, obviously you would have symmetrical study. Now, I mentioned to you earlier on that there are some things that could also cause asymmetry when you do your funnel plot, aside publication bias. So considerable heterogeneity could also be another cause for an asymmetrical funnel plot. And then chance, just chance, could also be another cause of asymmetrical funnel plot. So you might want to consider that. Now, this is the graphical method of checking for asymmetry. The statistical method of checking for asymmetry is the Eggers test, like we discussed earlier. So the Eggers test is another method of checking for asymmetry. Now, for us to run the Eggers test is also pretty straightforward on SPSS. Just click on Analyze, Meta-analysis, Binary Outcomes, Pre-calculated effect size. Are we there? If you are
Yes,
there,
sir.
just go ahead and click on Bias on the right-hand side. Check the box that says Eggers regression-based test. Click on and click OK. So you should have your Eggers regression-based test coming up. Let me see if that's already on our screen. Okay, thank you so much, Dr. Abiy has done that for us. So we can also see the result of the Eggers regression-based test there on the screen. So how do we interpret it? If the p-value that you have for the Eggers test is greater than 0.05, it means it suggests that there is no publication bias. So the Eggers test is just to check again for you to check your funnel plot to see whether the funnel plot is asymmetrical or if it's symmetrical. And the p-value that it gives you, which is really, really easy to interpret compared to looking at a scattered plot, makes it a lot more tempting and enticing to use to check for publication bias. So a p-value of more than 0.005, sorry, suggests that there is no publication bias. And here, what's our p-value?
Our p-value is 0.953.
So do we have publication bias or not?
No, we do not.
No, we don't have, sir.
All right. So another concept that we need to be familiar with is the trim and fill analysis. Now, what does the trim and fill analysis does? What does it do? Someone was about to ask a question. Okay, I guess you can go on then. So, what's the trim and fill analysis? A while ago, a group, about 2 or 3 epidemiologists came together and said, okay, if we have an asymmetrical funnel plot, I mean, what can we do about it? How can we identify these studies that are sort of making these plots asymmetrical, and what can we do to correct it, in quotes? What can we do to correct it? So what the trim and fill study does for you, the trim and fill analysis, what it does for you is it sort of removes the studies that are outliers, those studies that are the weird studies, the ones that are making your plots look asymmetrical. It takes them out, okay? It runs the meta-analysis all over again. It now adds some, let me use the word artificial studies. Now, these studies are not artificial per se. The calculations are based on some other things that are outside the scope of this study, but then it sort of calculates, does some calculations for you, and then fills in those dots in the funnel plot, fills them in towards the middle, okay? And then recalculates another, does another meta-analysis for you, does another funnel plot for you to sort of recalculate another effect size estimate. So this gives you an idea as to the number of studies that are responsible for the asymmetry that you are having, okay? And then, it's just a method to sort of, I'm being careful with using the word correct now, to correct for publication bias. It just helps you check for it too, okay? So I'll go ahead and explain again. The trim and fill analysis, sorry, removes outlier studies from your funnel plot, okay? Having removed outlier studies from your funnel plot, it replaces them with what I call artificial studies, okay? And then does a recalculation all over again for you to generate another effect size estimate. Now, the trim and fill analysis does not take into consideration other causes of an asymmetrical funnel plot. It doesn't. So aside publication bias, it doesn't take into consideration other things like maybe heterogeneity or chance that can be responsible for an asymmetrical funnel plot. So you also want to be careful in interpreting the results that you get after doing your trim and fill studies. So we can go ahead and just do a quick practical of the trim and fill studies actually. So still the same thing that we've done before. I want us to click on meta-analysis, analyze.
Hello, sir.
Yes.
Hello. Sorry, please. Sorry to interrupt. I have a question.
Yes.
Now, concerning the Eggers test, now
Yes.
there were two p-values. Which one do we interpret? Is it the one for the intercept or the one for the standard error? Because I don't know, I think I've come across somewhere that it's the intercept that you interpret, not the standard error. But I just want to clarify that.
I'm coming, let me just go back to the table.
Yeah, I think it's on the screen at the moment.
Yes. So you interpret the p-value for the intercept.
Okay, so because if it's for the intercept, then that means there's publication bias, because the p-value here is 0.01.
It's 0.01, which is
less than 0.05.
Which is less than 0.05. Yes, that's correct. That's correct.
Okay.
That's correct. Thanks for pointing that out.
Thank you.
Okay, so let us quickly run our trim and fill analysis. We are gradually coming to the end of the class. We have very limited time. So, given that we've just done previous meta-analysis, so we can just go ahead and do the same thing that we've been all over again. Meta-analysis, binary outcomes, pre-calculated effect size, and then you will see trim and fill on the right-hand side. You will see trim and fill on the right-hand side. So just click on trim and fill. Check the box that says estimate number of missing studies, and then click on continue and click on OK. So is Dr. Abiy still with us? Okay, yes. All right, so we can see the effect size estimates for the trim and fill analysis. Now, we can see that we have two rows there. We have observed plus imputed. Now, in this case, no study has been taken out or put in particularly. So you can see that the results are essentially the same thing. We have the same result for the observed. We have the same result for the observed plus imputed after running our trim and fill analysis. Now, the next thing we are going to do is just talk briefly about cumulative analysis. Now, the cumulative analysis just checks whether the magnitude of our effect estimate, our pooled effect estimate, whether
sorry, sir.
Yes.
How can you interpret the interpretation of this one?
So what you're looking for is you are checking if after doing your trim and fill analysis, you want to see whether or not there are differences in what you get, observed over and then observed plus imputed. Now, if you have a study where a trim and fill analysis was actually done, where some studies were taken out and where they were replaced with some other artificial studies, under this section that says number of imputed studies that we have as 0 here, you would actually see a number there. It could be 2 studies, it could be 3 studies, it could be 4 studies. But in this case, nothing was taken out, nothing was replaced. So that's why it's 0. And you can see that the number of studies in both of them are the same thing. The effect size, the same thing. Under this observed plus imputed, if some studies were taken out and replaced with some other artificial studies, the effect size will probably change here. The standard error could change. All of these figures below could change, okay? But because that has not been done in this case, the figures are somewhat the same thing. They are exactly the same thing. They are identical results that we have here. Is that clear? Okay, let's move on. All right. So let me just go back to sharing my screen so that we can just look at the cumulative analysis. Okay, since we are going to run it, I think Dr. Abiy should just continue with the screen instead. So we are going to do what we call cumulative analysis. What does cumulative analysis do for us? It checks whether over time, over years, whether there has been a change in the magnitude and direction of the pooled effect estimate. We want to know if it has changed. So what cumulative analysis does is it sort of groups all the studies into different years. And then after sorting them, arranging the studies into different years, It adds a study per time, does meta-analysis, adds another study from another year, does the meta-analysis all over again. It continues like that until it gets to the most recent studies. I would explain again. So for cumulative analysis, it sorts or arranges your study in the order of the years, okay, from the least recent to the most recent. And then it keeps adding a more recent study per time, and it will run the meta-analysis all over again, okay? So it's something that is better seen for you to appreciate it actually. So we are just going to do it together. So I want us to click on Analyze again, all right? I want us to click on Meta-analysis, click on Binary Outcomes, click on Pre-calculated effect size, okay? And then I want you to click on Analysis on the right-hand side in those blue texts. Click on Analysis, and then under Analysis, you will see Cumulative Analysis there. Okay, you see cumulative analysis there. So that is what we are interested in. All right. So under the cumulative analysis, put in your year. Put in your year. And then check cumulative effect size. Okay, check the box. Click on Continue. Oh, we should check the box for confidence intervals too. Sorry. So check the boxes for confidence interval as well, because we need the confidence intervals so that it just shows us. Yeah. So check the boxes for confidence intervals as well. Then click on Continue.
Okay.
And then go to Plot. Click on Cumulative Forest Plot. Check the box that says Cumulative Forest Plot. Under Display Columns, check Cumulative Effect Size, check Confidence Intervals, and under Variables, the section that says Additional Column, put in Year. Continue. Okay. And you should have your cumulative forest plot. Do we all have it? So Dr. Abiy has put up the cumulative forest plot for us to see. So we can see that it has arranged the studies starting from the oldest study to the most recent study, all the way from the top to the bottom. So what you expect really is for the last study at the bottom. That last study at the bottom, the effect size estimate that you have for that last study and the confidence intervals should be the same thing as the effect size and confidence interval for your main meta-analysis. And if you go and check, you see that they are actually the same thing. So you will see that as the years have been going by, the confidence intervals have been narrowing. The confidence intervals have been narrowing until you get to the most recent study. So again, let me just look in the chart. So again, what happens is it sorts your study in order of based on the years. You have the oldest studies at the top. You have the most recent studies at the bottom. So your cumulative forest plot or cumulative analysis adds a more recent study each time and does a meta-analysis each time over and over and over again until you get to the last most recent study. And when you get to the last most recent study, what you have under the logarithm of the risk ratio, the upper and lower confidence intervals has to be the same thing with what you have in your main meta-analysis. The results are going to be essentially the same thing. Okay? So that is what your cumulative analysis does for you. All right. So we have looked at a couple of things in this class. I understand that things could be a bit confusing, but then it gets better when you start to actually do these things by yourself and then just, play with things and see exactly how things work out. So we have looked at the fixed effect and the random effect meta-analysis. We have looked at forest plots. We have talked about all of the things we see on the forest plot and what they mean. We touched briefly on confounders. We touched briefly on what confidence intervals mean. We explained all of the things that the forest plot, the things that you find on the forest plot. Somebody said, what does tau squared and h squared mean? I don't think you should be too bothered with that at the moment. All you really need at this time, I think, is just this I squared and just know your Q statistic for heterogeneity. Then we have also looked at the funnel plots, how to check for asymmetry graphically with the funnel plot, and how to check for asymmetry statistically with the Eggers-based test. We have looked at the trim and fill analysis and what it does for us and what we expect to see when we do a trim and fill analysis. We have looked at how to interpret different results based on different effect sizes. We looked at when you use a null value of 0, when you have mean differences. We looked at when you use a null value of 1, when you're dealing with ratios instead. We also looked at heterogeneity. We looked at how to check for heterogeneity. We looked at the two methods. We looked at the limitations of one of the methods. And then we looked at why you should be careful with how you interpret your heterogeneity results or your I-squared statistic results, because sometimes it doesn't take into, so we also looked at prediction intervals. We looked at why one study may stand out compared to the other studies and what you should do when that happens. We also then looked at bias and sensitivity analysis, publication bias basically, and then we looked at the trim and fill analysis as well as the cumulative analysis. So I think that's about everything.
So we have a question.
Okay.
So someone asked, so this cumulative forest plot that you have, what happens if the number that you find is different from the number in your main analysis? What do you think will be responsible?
So I don't think it should be different.
Yeah.
I mean, it should be the same thing.
I mean, my expectation would be that it will be the same, and that if it's different, then maybe there's an error along the line.
Shouldn't be different.
So in this case, it's exactly the same, but if a person finds different numbers, most likely there's an error, in their work, and they should just check it again. That's what I would think. Okay.
All right. Do we have any more questions? Okay, so I reckon using SPSS is actually very straightforward compared to some of the other methods that you might have tried. Although those ones are a lot more, detailed. You can do a lot more with them. But for those of us who are just starting out, I think SPSS might not be too bad. Francis Fagule, please go ahead and ask your question.
Thank you very much. I just want to ask, especially maybe from Dr. B, we did RevMan yesterday, and I noticed that quite a number of the things that you have done with SPSS, we didn't do it with RevMan. I want to be sure, is it a limitation of RevMan, or we have not gotten to that stage? That's why, like this cumulative, some of the things that you showed us today. Thank you.
Yeah, so it's both. So the way we did the RevMan class was that we went slowly and tried to explain some concepts in more depth, okay? And we spent a lot of time on the dichotomous variables. We have not even gotten to the continuous variables in RevMan. So we have not done heterogeneity. So we haven't gotten to a lot of the things that we have shown today in SPSS. That's one. But there's also the issue that with RevMan, there are limitations. So for instance, RevMan cannot do cumulative meta-analysis. You might be able to sort your data by year, but I don't think that will show you how the numbers have changed if you were pulling. Like some of the things that we have done here today, you will not be able to do in RevMan. So heterogeneity as well, RevMan will show you the I-squared and I think the Q statistic, but you cannot do meta-regression in RevMan. You cannot obtain prediction intervals. And we'll talk about it next week. What you can do instead in RevMan is subgroup analysis, which kind of gets at what you will be getting for prediction intervals, but not exactly. So we'll talk about that next week, Saturday or Sunday.
Okay, thank you.
Yeah, thank you so much.
You're welcome.
Any further questions?
Any other questions? Yeah.
Okay, I can't see any more hand raised.
Yeah, please, sorry, I don't know if you can explain the interpretation of this I-squared and tau squared again, please. Thank you.
So the I-squared statistic, we said we use it to check for heterogeneity, didn't we? Yes?
Yes, sir, yeah.
All right. So what part don't you understand exactly?
That's how we want to interpret this 0.82.
Okay, so 0.82, that's about 82%.
That's 82% difference between the included studies.
So for the I-squared statistic, you sort of interpret it based on the values that you have. So you have different categories. You have the limited heterogeneity, you have moderate heterogeneity, you have substantial heterogeneity, and you have considerable heterogeneity. So 0 to 40%, if you have 0 to 40%, that is limited heterogeneity. In this case, we have 0.82, which is sort of like 82%. So that's considerable heterogeneity. So when you have that considerable heterogeneity, you want to find out what is responsible for that. What has caused this heterogeneity? That's when you go ahead and do your prediction intervals. So when we did our own prediction intervals, we realized that it was the Tanzania study that was included that had that significant prediction interval of less than 0.05. So it was most likely the study that was responsible for the considerable heterogeneity that we got when we did our first check for the heterogeneity. So the first step is get your I-squared, which is checking for heterogeneity. If the heterogeneity is considerable, then go ahead and just do your prediction intervals to check for what is responsible, which of the studies is responsible for the heterogeneity that you have. Okay?
Yeah. Okay.
So
when you find out, do you now remove the study or what?
So when you find out,
it's in mind.
Now, it all depends on what you are working with. If you have, if this study, for instance, as I explained before, if say 6 studies, after doing your prediction interval, you see that one study stands out very differently. When you go ahead and check the characteristics of the study, maybe the population characteristics of the study and all of that, you can find some fundamental differences between that study and the other studies in your meta-analysis. In this class, for instance, we said a number of things could be responsible for Tanzania having that prediction interval. It could be because of the design of the intervention. It could be because, okay, maybe in their own study, what was given subcutaneously, while all of the other studies were given intravenously. It could be because Tanzania decided to just recruit only children, while the other studies recruited adults. So all of this will give you an information, an idea whether or not to include this study in your meta-analysis. And as I said before, if all of the studies have recruited elderly people and there's just one study recruiting children, it might not make a lot of sense for you to go ahead and include that study in your meta-analysis. If you have 50 studies that have looked at giving a medication subcutaneously, and one study is looking at giving it intraosseously, it might not be very wise for you to go ahead and include that study in your meta-analysis. So I think Dr. Abe wants to add something as well.
Yeah, I was going to, but I figured maybe it wasn't necessary. I realized that I was going to potentially confuse the class. So I think one of the reasons why we have had a number of questions about heterogeneity is because we haven't gone over it. This is the first time people are coming across it. And
Okay.
yeah, and as far as the recordings that we shared, we didn't ask people to look at those recordings yet. So you will have opportunity to clarify what to do with heterogeneity over the next week or so. There is an entire video on heterogeneity, influence analysis, and all of that in the recordings that we shared. And when we do the Revman class again, we'll explain it in more detail as well. So if you're still confused, we can talk about it again next week.
All right, thank you so much.
Thank you very much, Dr. Oyadiran. This has been excellent.
Thank you.
Any final questions, thoughts before we close? So we have Makinde. Please ask your question. If you have a question, just unmute yourself and please.
Just ask. Go for it, Makinde.
I think he has lowered his hand. Maybe it's a legacy hand or something. Maybe it's old. Any final questions? None? Okay. Thank you very much, everyone. Look forward to continuing the conversation. And if you have any comments about the classes, anything you want us to change, any aspects you want us to go over again, please let us know. And we'll try to accommodate as best as possible. Thank you, everyone. Have an excellent week.
Thank you.
Thank you so much. Bye.
Bye.
Thank you.
Thanks
Bye-bye.
a lot, sir. Bye.
Thank you. Bye.
Thank you very much.
Thank you very much.
Thank you very much.